I apologize for the wait today. I've had a morning already. The guy in front of me as I was driving here, his tire exploded. And then I got stuck behind a truck that was going 15 to 30 miles under the speed limit. And then YouTube changed their interface, so I have no idea how to use anything anymore. Yay for being tech literate. Okay, so I'll stop making excuses now. I'm late, and I apologize. Today what we're going to talk about is we're going to discuss logic gates. So we've been talking about an OR gate, an AND gate, a NOT gate, an XOR gate, and an equivalence gate. And all of these are great by themselves, but we can use them in tandem with each other. With all of these gates, like let's say we take an AND gate, A, B, and C. The input to this is either a 0 or a 1. It's either an off or an on. It's either a true or a false. Okay? The output of this is a 0 or a 1, an off or an on. It's either a voltage is applied or there is no voltage, or at least a reduced voltage. So with this, we can take one of these and plug it in like this. Okay? And if we do this, we've created a brand new circuit entirely. So let's say this is A, B, C, D. We'll call this E, F, and we'll call this G. Now this is a little bit more complicated than what we've dealt with before. Okay? So if I'm going to draw my truth table, A, B, C, D, E, F, G. Here, A, B, C, and D are my inputs. I have 4 inputs, so I'm going to have 16 entries in this table. 0, 1, 1, and 0, 1. Okay. You can see that. Nice. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. So that's fun to draw. What we know about this is that G is on if either E or F is on. So for us to try to figure out G, which is probably the ultimate output of this system, that's a G, I don't know if it shows up very well. For us to figure out what G is, we need to know what E and F are. So we'll start with E and we'll start with F. Okay? E only depends on A and B, meaning these 2 columns don't even matter. If you were to only look at this, shake my arms, so it's like, yeah, there we go. These 2 columns don't matter. E only depends on those 2. So if both of them are on, which are these 4, then E is on. 1, 1, 1, 1. Otherwise, they're zeros. 5, 6, 7, 8, 9, 10, 11, 12. Okay? F is the same way. If C and D are on, it's on, but that's it. There's no other case. So once again, it does not depend on A and B. The output F only depends on C and D. That's it. So C and D, F, we got 2 1s here, 2 1s here, 2 1s here, and 2 1s here. And we got zeros in between. Okay? And then G is if we have a 1 in either F or E, we get a 1 here. So here this is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 1. Okay? How many 1s do we have total in this column? 1, 2, 3, 4, 5, 6, 7. Okay? This is not, it's not a truth table that we can get by just saying, oh, well, it's just one gate. No, this is now much more complex. It's going to require multiple gates simultaneously in order to make this work. Okay? So truth tables can be a lot more complicated. So we'll just keep playing around with that now. Let's say for this truth table, what we have now is, I'm just going to go ahead and leave this up here. Just to save me time. Also, I think I'm going to draw on a black marker because I'm not sure I like the blue. Okay, let's say we have only 3 inputs. And this is a not a NAND. So this is NOR, NAND, NOR. Okay? And we've got A, we've got B, we've got C. Now here, A, B, and C, B is in both of these. So the inputs of this NAND gate depend on B, and the inputs of this NOR gate also depend on B. We'll go ahead and call this D, this will be E, and this will be F. So dang it, I have to rewrite my table. I was doing so well. Okay, so A, B, C, D, E, F. Here we have 3 inputs, which means we're going to have 2 to the 3rd entries. And our truth table, 0, 1, 0, 1, 0, 1, 0, 1. Boy, that's a lot easier to write than 4 entries. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Okay? Now, D is only on if both A and B are off. So here, if A and B are both 0, D is 1. If either one of them has a 1 in it, it's 0. E is now here, if both B and C are on, E is off. Otherwise, it's on. So if both B and C are on, this is a 0, this is a 0. Okay. And then F is if either one is on, then it's a 0. So we go back through here, and it's this is a 1, and this is a 1, and everything else is a 0. Okay. So this is just a little bit of how to do logic gates in series. If we combine these logic gates, we can come up with a much more complex truth table, where now here, this is a more complex outcome. But as we'll see later, we can actually reduce this into a much simpler form if we know, if we understand a little bit of Boolean algebra. So what is Boolean algebra? Okay. Boolean algebra. Well, these are logical functions that allow you to do math. Imagine if 1 plus 1 equals 1. That's Boolean algebra. If a 1 is present, you get a 1 as a result. Okay? Except for these aren't ones and zeros as we understand them. They're trues and false. They're presence of a voltage and absence of a voltage. Okay, so it really ends up being true plus true equals true, instead of 1 plus 1 equals 1. But writing 1 plus 1 equals 1 is a perfectly valid way of approaching this. So with Boolean algebra, the important thing to note is we have basically 3 different functions inside of Boolean algebra. We have function 1, which is addition. Okay, A plus B equals C. Now the idea is if either of these are 1, C is 1. Okay, this represents an OR gate. If either A or B are 1 or true, C is 1. Okay, so that's our Boolean algebra statement number 1. Boolean algebra statement number 2. A times B equals C. Well, this means if either of these are 0, the C is going to be 0, because 1 times a 0 is 0. But if both of these are 1, C is going to be 1. And this represents an AND gate. If both A and B are 1, C is 1. Okay? Oh, I guess there's more than 3, but let's say now A naught equals B. This is a not sign that basically says that this is a not gate. Okay? If not A, then B. Okay? So if A is not true, then B is true. If this is a 0, then this is a 1. If this is a 1, then this is a 0. Okay? And then the last one that we're going to talk about is this is a exclusive OR B. That's what makes this an XOR gate. If either A or B, but not both, then C is 1. Okay? So we've got our 4 different functions. If we take this and throw a not on top of it, we're just combining these two, we've created an OR gate. Okay? If we take this and put a not on top of it, we've created a NAND gate. We take this and put the not on top of it, we've created an equivalence gate. So these 4 functions basically are how we derive all of our Boolean logic statements. Okay? Now Boolean logic it's a different way of writing these logic gates. So let's say I'm going to say A, B plus C, A, B, not. Okay? What does this mean? And we'll say this is equal to D. What does that mean? Well, it means this is true. If this condition here evaluates to true, or if this condition evaluates to true, then D is true. That's what the addition sign says. So since there is an addition sign, we know that as long as one of these turns into a 1, D will be true. And this just says since there is an addition sign, we know either condition can evaluate to true, and D will be true. I do not know if you can read that. I can't, but some of you are much better at reading than I am. So since there is an addition sign, we know either condition can evaluate to true, and D will be true. Okay, so if this or this, the plus sign signifies that it's an OR gate. If this or this, then D. Okay, so what we need to know is how do we now write this? So if I erase very small handwriting. In order for this to be true, this is an AND gate because they're multiplied by each other. And that means, and this is a not sign. Now here the not sign only goes over the top of the A. Okay? So this statement, if we were to write it out, is if not A and B. Okay? So if not A and B. If A is not on and B is on, this creates a true statement. So if we were to draw that out, this has a NOT gate on it, this has nothing on it, and this goes into an AND gate. Okay? So if not A and B, then output 1. Okay? Well, what about this one? If we were to write this one out, it's if not C and B and A, if not all of them, man, I'm writing really small here. Okay, so if not all 3 of them, then it's true. Okay, so we know that because it has a not on top of it, if we were to take off the not, we just have an AND gate. So this is a NAND gate. Okay, it is a not AND. So we can write it as one of these. Doop, doop, boop. Got our C. Okay? And then these go into an OR gate, which comes to a D. Okay? So that's what our logic system looks like. Okay? Here, not A and B. So here, not A and B. Or CAB not. So C and B and A not. And then they combine in an OR gate to form D. So it's a little bit more complex of a system, trying to now take Boolean algebra, which is this, and then writing it as this. However, this gives us a lot more capabilities if we're going to write Boolean algebra out as this system. Here, this is a physical system. If I wanted to build this, I can. This is not hard for me to build. If I wanted to build this, well, I can, but this is much more abstract. It's like this is a mathematical representation, and this is the physical system we built. Here's an AND gate. Okay, you plug in 3 inputs into an AND gate. Here's another AND gate, except there's a NAND gate. Here's a NOT gate. Here's an OR gate. Those are all physical components you can purchase from an online store. You can plug wires in. You can make it work that way. This is much more abstract. Okay, So we're going to continue to develop the idea of Boolean algebra. Why? Well, because Boolean algebra is going to give us some opportunities when it comes to Karnaugh maps. Okay, Karnaugh maps they were in your reading assignment. We will talk about them on Thursday. We're not going to talk about them today because they're a little bit above what I'm hoping to get at today. I really want to solidify the idea of Boolean algebra. Okay. So we'll keep going with Boolean algebra. Here, we know we can take what we had. I could have taken that system. I could have drawn a truth table from it. It wouldn't have been that hard to do. It's just a truth table. But I'm going to take another Boolean algebra statement and I'm going to throw it at you. Let's say we have not A, B, C, not D, not is equal to E. What does that mean? Not A, B, C, not D, not. Well, let me write this a little bit bigger. Okay, what I meant by that was let me write it the same size, but I'll just say I'm writing it bigger. So not A, B, C, not D, put it in parentheses, and then we not the whole thing. Okay, so I'm just writing the same thing, this time actually bigger, equals E. Okay, so not A, B, C, not D equals E. What does this do? Well, first of all, we know that this goes through a NOT gate. Okay, we know all four of these are multiplied by each other. So if I'm going to write this out, this is not A and B and C and not D. Okay, and then I'm going to throw all these in parentheses, and then it's not that. Not A and B and C and not D equals E. This is not a grammar class. Okay, you know I love grammar and I love writing words, but Boolean logic is not grammar. This would drive people crazy. So we have not A and B and C and not D equals E. Okay, just writing this out. We know this statement right here, this piece is right here. This piece right here goes right over in front of the A. It is a not A because it is directly over the A. It is a not A. This piece right here goes directly over D. It is not D. Okay? And then we're taking the entire function and we're knotting it. So there's not the function. Okay? Since these are all four multiplied together, this is an and. Okay? This is one big Nand gate because it's a not and. And inside of that not and gate, we have two individual features that both have been negated, reversed. So if I take my A, B, C, D, A is going to have a not gate on it. D is going to have a not gate on it. B and C do not have those. Okay, and we'll take all four of these and we will put it into a NAND gate, and there's E. So the way that we represent this function, clean it up a little bit, start drawing lines all over it. The way that we represent this function is using this gate. Okay? And all we do is we look at this, we write out the words. This is not A and B and C and not D, not. And then from that we can see this is a NAND gate where we have two different nots inside of it. Okay? Or sometimes some people can just jump straight from this to here without writing out the words. I don't write out the words. Then again, I also eat hot dogs for lunch every day, so don't always have to be me. All right, we'll keep practicing. So this is that. Okay. There's math involved. There's a delicious equals sign. It's pretty hot. I like the way that I wrote my D. There's a nice swoopy on the bottom of it. It's right there. I don't know if you can see that on the video. There are marker flecks on my board. There are marker flecks on my hand. So how do we do this? Okay. First of all, just like real algebra, you start from the innermost parenthesis. Okay. So we go inside the parenthesis and we say, what's inside here? Well, this is A or B. That's what the plus sign means, or. A or B or C and D. Okay, C is multiplied by D, therefore we have to put the and in there. Okay, that's everything inside the parentheses. Now we're going to put this back in parentheses, and we're going to put this in front of it. Not that. Okay, now I can say right here we've got some plus signs in here. Because we have the plus signs in here, this is a not or gate. This is an or gate. Okay? So we know, let's go ahead and write just this into an or gate. So we got this. We have, let me write this a little bit bigger. Need a bigger OR gate because I got to get a lot of inputs in this. Okay, so we have A, we have B, so A or B or C and D. Okay, so this right here represents CD. How do we get that to represent CD? Well, we have to put this as C and D. And there's an AND gate here. We have to include an AND gate. There's an AND gate right there. We just put an AND gate right there. That's an AND gate. Wow, that is a really poorly drawn AND gate. Kind of looks like okay, that did not get any better. You know what? This is an art class. So here, this AND gate produces CD, C and D. Okay, so we've got C going into it, and we've got D going into it. Okay, so C and D go into the AND gate. What comes out is C and D. C and D goes into the OR gate, because we have these two ORs. We only have three inputs to the OR gate, A, B, and CD. A, B, C, D. Okay, and what this gets negated with a not, and it outputs E. Boolean algebra. Okay, so let's keep going. Let's do a harder example. You know, I'm all about those harder examples. So let's say we have now, let's see, we're going to make it A naught B plus C, put this in parentheses, C naught BA plus BA naught. And that equals D. A naught B plus C in parentheses multiplied by, in parentheses, C naught B A plus BA naught. So we start with the innermost parentheses. Okay? Here we've got parentheses. We're going to write this out as this is not A and B or C. So we've got not A and B, both of these multiplied by each other, or C added in. Okay? We'll go ahead and throw this in parentheses. Now this parentheses is multiplied by another parentheses. Multiplication is an AND gate. So we say and, put down another parenthesis. This is not C and B and A, or, because there's a plus sign, and then this is a NAND gate, okay? It is B and A, not. So I'm just going to go ahead and say B NAND A, end parentheses. So this one's a little bit more wordy to write out, okay? And if I'm going to draw a logic gate from this, how do we do that? Well, we know coming into this one is not A and B. So we know that there is going to be one gate that puts out this. Okay. These are added with an OR, which means this is going to go into an OR and then output this. Okay, so we've got this parenthesis covered. We now have this statement. This is going to also connect to C. So we've got A. Okay, so just this creates this statement. Not A, not A, not A and B, not A and B or C. Just getting more and more complex as we go. Okay, and then we take this, and this has to go into an AND gate with that function. So let's build that function here. Okay, so we have not C and B and A. So you know what, I'm just going to write all of these three again just to keep it clean. So we've got an AND gate. The AND gate produces A, B, C naught. Notice I'm switching the order of the values. You can do that in an AND gate. You can do it in an OR gate too. You can switch the values around. As long as I'm not saying CBA, ABC, not, and then I decide to switch A over into a different one now, and you can't do that. As long as this stays the same term, X times Y times Z, Z times Y times X. As long as it stays the same term, you can do that. Okay? There is equivalence in Boolean algebra. So I've now named this ABC naught. I'm going to go ahead and bring A, B, C, and then I'm going to not C so that it comes in ABC naught, A and B and C naught. Okay, that's this term. I need this one, and they have to be added together. So I'm going to create another OR gate. And going to pull this out, and we have not B and A, or B NAND A. So I'm going to go ahead and create a Nand Gate and put A and B in here. Okay, and this creates AB not. Okay. This statement here, since it's an OR gate, creates an A and B and not C, or A and or not A and B. So this is A, B, C not plus A, B not. You'll notice that's this. We now have this statement here. We now have this statement here. And then we have to multiply them together. How do we multiply them together? That's an AND gate. Okay, so multiplying these two together with an AND gate produces A not B plus C, A, B, C not plus not AB, which that is equal to D. So that is our giant ugly equation that we've come up with to build D. Okay, now each of these is a buildable solution. If you have a NOT gate, you have what, 1, 2, 3 AND gates, 1 NAND gate, 2 OR gates, you can make this. You can build it. Just wire it up. That's what it takes. Okay, all of this Boolean algebra, it gets, if you break it down into what pieces go where, how do I make this piece? How do I make this piece? And then once I have this piece, how do I make this piece? Once I have this piece, how do I make this piece? Okay, you break it down into pieces, this kind of falls together. It should be fairly simple. You will have several assignments in your homework related to breaking these down, taking this, and building this out of it. Okay, but what if we want to go the other direction? How do I create a Boolean algebra statement from a logic gate circuit? So let's say I've got A, B, and we've got A. Here's an AND gate, so this creates an AB. We've got C, goes into a NOT. We got a D, goes into a NOT. We got this, goes into a NOR gate. So this becomes C NOT, D NOT, NOT. And then this goes into a NAND gate. Okay. What is the output there? Well, again, what I've done incrementally, and I shouldn't have because it makes it a lot simpler, but it's good practice, is I've actually written out what the outputs individually create. So this creates output E. Well, here, we know this line here coming in is A. This line in coming in is B. Okay, so this is just A, this is B. The output of this, because it is an AND gate, is just those two multiplied by each other. Here, the input to this is C, the output is C naught. The input to this is D, the output is D naught. I don't know if you can read that. Oh well. So we've got C naught, D naught. The input here now is C naught. The input here is now D naught. As those lines, they're the same. D naught here, that's D naught there. If D is not on, then that is producing an on signal. Okay, so we've got C naught, D naught, and it's going into an OR gate. This becomes C naught plus D naught. And because this is a NOR gate, that becomes a NOR. I wrote that wrong first. So that is not C or not D, not. And we got our AB here. Here going in, this is, again, AB. It's the same thing coming out of the AND gate. And we've got C naught plus D naught naught going into here. This is an AND gate, which means we multiply them together. This is a NAND gate, which means we then take the naught afterwards. I'm going to need a little bit more space. So to write this bigger, this piece right here coming out of the AND gate going into this is AB. Okay, I'm going to go ahead and put that in parentheses. Okay, we then take this piece coming in here to the AND gate, and this is not C or not D naught. So we'll put that in parentheses, C naught plus D naught naught. Okay, great. This is now we've put it into an AND gate. Now this is a NAND gate, which means we throw this on top of it, and that's equals E. So it is AB in parentheses, not C plus not D not, end parenthesis, not over the entire thing. Boy, if that isn't fun. Good has been done here. I would suggest that you spend some time understanding this. This is not intuitive to most people. I don't think it's the hardest concept in the world, but trying to get Boolean algebra, trying to understand what Boolean algebra means, and actually be able to build something out of a Boolean algebra statement, it's a really important skill, particularly for this class. You want to be able to understand logic gates, you've got to understand Boolean algebra and how Boolean algebra turns into logic gates. How we can pull logic gate systems out of a Boolean algebra statement, or how we can pull a Boolean algebra statement out of a series of logic gates. And being able to combine those two is a good endeavor. You have a quiz from last week. You have a reading assignment, and yes, a reading assignment and a homework assignment. Those are all due tonight, midnight. Good luck. Feel free to email me if you have questions. We're going to be talking about Karnaugh Maps, and I'm going to give you a new quiz this Thursday. Okay? So have a good next 2 days. Bye.